happy to have Rina Anno, who will speak about Hochschild homology of noncommutative symmetric quotient stack. All right, please.
Right. Thank you for inviting me. And let me first start with the history of the question and why why I'm calling this a noncommutative symmetric quotient stack. So let us look at a smooth affine variety with an action of a finite group, and then its Hochschild homology of the Rhin smash product with a group can be expressed as a Hochschild homology of the function rings of the invariant subvarieties of X.
Hochschild or cyclic?
This is cyclic. So cyclic homology with coefficients in some module W.
Do you remember why they asked that question?
Why?
Yeah.
Why? Why that? Well, because what's on the left? It's the well, it's so it's the equivalent cohomology with respect to G. This is orbifold cohomology of X quotient by the action of a finite group G.
So alpha is
the action. So yeah, so this A sub alpha denotes so equivariant under the action alpha of G. So and then this result can be generalized to a smooth quasi-projective variety. So from a smooth affine variety to a smooth quasi-projective variety, where the quotient is sufficiently good. So it was done by Baranovsky, and it is cyclic homology of space of of the category of the G equivariant vector bundles compared to the direct sum over the elements of G of cyclic homology of the category of on G invariant subvariety for every G. And we're note that we are also taking the coinvariance under the action of G here. So yeah, I can scroll, but I cannot. So it looks like no, I can write, but I cannot erase or switch the color of what I write. So we're taking.
Will you consider only finite groups?
Yes, on the finite groups. So because so we're taking a direct sum over all groups of G, coinvariance under the action of G. So this this is about the orbifold situation. So a variety X, we're taking a quotient by a finite group.
I try to understand the left-hand side, the vector G. Is that the modular space of vector bundles on X, G equivalent vector bundles on X, or?
This is so I believe this is G equivalent K theory.
Sorry, I mean, this is a Hochschild homology, so this is just should be of some category, and this is just essentially DG enhancement of the derived category of G equivalent vector bundles on X. Because we are smooth, G equivalent vector bundles are the same as G equivalent coherent sheets. So essentially, this is a G equivalent derived category of X.
I see. So it's not the earlier classically that's algebra. Now you replace the algebra by the
Yes.
Classically
by
it's
the tensor
a
category. Mhm.
Yes, because in the affine case, it's an algebra. So in a quasi-projective case, it's now a category of sheaves on X. And this decomposition has been recently generalized to DG categories. So instead of cyclic homology, we just take Hochschild homology. So Hochschild homology of so if we have a finite group acting on a DG category, then Hochschild homology of the G equivariant category is isomorphic to the sum. So here this so the right hand side here is slightly rewritten with respect to the previous two forms of the right hand side, but it is the same thing. So
can I
yes.
can I make just a small additional comment? I mean, Nordstrom result, the third result on this page, is only half of the previous two results. I mean, the special thing about the first two results is that on the left-hand side, we have a G equivariant, essentially, variety. We have an orbifold. And on the right, we have perfectly ordinary cohomologies. So orbifold, there's no orbifolding happening on the right-hand side. We just take invariant locuses of each element of the group and compute their ordinary cohomologies. So we express orbifold cohomology in terms of a direct sum of ordinary cohomologies of fixed point loci. But in Nordstrom's case, on the right-hand side, you have a Hochschild homology twisted by each element of the group. So the right-hand side is still very much in the realm of orbifold cohomology. And it's the sort of the second step which it turns those twisted Hochschild homologies into the Hochschild homologies of ordinary Hochschild homologies of fixed point loci. That's really the main point of the first two results. So I would say that Wille only generalized sort of smaller first half of those results by Gensler, Jones, and Baranowski, not the whole thing. But that's
yeah,
at least in my opinion.
I get.
So I have, you see, I understand that there might be interesting conversation between experts, but for people from outside. So first, I do not understand why do you need to consider an additional this. I even cannot say. In the first line, it's I module W. In the second line, I even do not understand what you are talking about. It's just cyclic homology
It's a
of some stack
module
or
over a
whatever.
category.
Hmm?
So W is a module over a
Yeah, but why?
category.
What's, I mean, I understand that you can generalize even
Yes,
further
so this the generality in which it works. But so for this, so this is the history of the question. So I'm just
but I have
listing the most
a
important
question to the history, all right?
Okay.
Because Hochschild homology, they are functorial, so my question is either a semi-orthogonal decomposition for the last line. Yeah, so that's...
No, this is a Hochschild homology thing. This is not a functorial thing.
Hochschild homology is a functorial thing, so maybe...
Yeah, but I mean this is not a decategorification of a functor.
Yeah, but my question is, because you see, there might be some results, people have their own motivation, but I would like to understand.
There is no semi-orthogonal decomposition underlying this Hochschild homology decomposition. It's well known that there isn't one. I mean,
okay, maybe it's well known, but not for me. All right, so then you say that there is no semi-orthogonal decomposition, just
Yes.
okay.
Yes.
All right.
And then let us consider a specific situation where say in the commutative case, the variety we act upon is a direct product of several copies of X, and the finite group acting on it is Sn. Note that it's okay. So Sn acts on direct product of X, and then so it has been so it has so I'm actually given only a brief history. There are many names of people who contributed to this theory, but in particular, so if X is a direct product of several copies of a variety and Sn is the symmetric group, then for every G is a product of non-intersecting cycles, and the variety that is G invariant, so that so this thing is just several direct product of several copies of X embedded as a direct product of several diagonals. So every X upper index G is isomorphic to several direct copies of X. And then one can rewrite the right-hand side as so as a sort of a symmetric, not so as a symmetric algebra whose basis is so several well, here we view Tc of T as a vector space with a basis T squared, T cubed up to to infinity. So we use them to
Normally
label
starts with T, not with T squared.
with T, yeah. So T squared, T cubed to infinity. So no constants. And the way we use them is that every element G corresponds to a product of several cycles. And then to every, so the variety, so the G invariant variety, X upper index G, is a isomorphic to several copies of X, and each copy of X corresponds to one cycle. So let T to the K denote the cycle of length K. And then to every such X to the G, so we have a direct product of several copies of X, and to this direct product we can associate a monomial of T to the K. But now we view each T to the power K as a separate variable.
Rina, do I understand correctly that when I replace K theory by cohomology, it's a classical result
Yes.
of MacDonald
Yep.
in the 60s? Yeah.
Probably, yes. Yes.
Before this much younger.
Before yeah. It has a long story.
Yeah, but actually that story of MacDonald led to him writing his famous book on symmetric functions. And probably you will use a lambda structure on the left-hand side as well. Yeah, okay.
Yes. Yeah, and then lately...
I just bother you again. So the powers of T is going to be corresponding to some degrees. And the degree here, you have the symmetric power, and also you have the K group.
Yeah, actually,
also have the degrees, right?
No, T has no degree.
Powers of T correspond to cycle lengths in the cycle decomposition of G.
It's exactly what MacDonald did. Yeah. So
yes,
because you have a decomposition of the symmetric power and the union of products of strata, which are parameterized by partitions of n, which are the same as lengths of cycles. So then T is just bookkeeping parameter.
Yes. Yeah. So T yeah, so we are not.
It is somehow corresponding to, I mean, this, you have the unfolds. So does that, and you have S up star and also K up dots.
Yes, so both sides are graded, but that degree on the right hand side comes from the K
Actually, both sides are bi-graded. Have unrunning.
Actually, it's a good point, because if the K-theory or whatever cohomology is set in degree 0, it would be just an obvious thing, but you
But
should
now
be
you have
a little bit more careful. Yeah, okay. Yeah, that's...
Yeah, so both sides is bi-graded, but I think this is an isomorphism of a total spaces of these bi-graded things. So for a fixed n, we are going to have monomials of different degrees. So fixed n spreads over several graded components in the symmetric algebra. Yeah, but t is a bookkeeping parameter, so we are never using any kind of structure on C of t. So we could just as well name them T1, T2, T3, so just labels. So yeah, and then quite recently it's been conjectured that a similar decomposition holds for Hochschild homology of a symmetric power of a DG category T. Now, in their paper, Belmans von Krug used the use the definition of symmetric power of T, introduced by Bondel and Garter, that
sorry, Kapranov and Gantner.
Kapranov and Gunter, sorry. Yeah, so Kapranov and Gunter as SN equivalent structure on T. But yes, so it was a conjecture for a smooth proper DG category for a similar decomposition for Hochschild homology. And then as we were working on it last year, so actually as our work was already basically complete, that we were sending it to experts to look at, we discovered that Ville Nordstrom was also working on the same problem, so proving the same conjecture. So they were two parallel works that finished, so unaware of each other, finished head and head. So Nordstrom proved this conjecture by constructing a roof of quasi-isomorphisms between the complexes. So the difference between our approach and his approach is that we basically low technology brute forced it, and we have an explicit isomorphism between Hochschild complexes.
So may I ask, so at the level of stacks of objects, well, assuming that it's sufficiently good DG category, so it corresponds what to isomorphism with spaces of differential forms?
Now I think it corresponds to the above, to isomorphism of K theory, so equivalent K theory.
I'm a bit confused. Probably I'm kind of too ignorant, but what K theory has to do with Hochschild homology?
Now, I mean, if X is an affine variety, so Hochschild Hochschild homology of the derived category of coherent shifts. I mean, we can compare K-theory of X to Hochschild homology of the derived category of coherent sheaves in X.
Rina, can I add just one
Sure.
thing to your remark? Siegel and Wang work with topological K-theory. So they have K0 and K1, and the total K-theory they work with is simply isomorphic to the cohomology. So and then so in our case, as it is well known, Hochschild homology is also via Hochschild-Kosten-Rosenberg is isomorphic to complex cohomology. So that's what this is all about, essentially.
Yeah, you see kind of motivation for my question, but it probably should be postponed, but I don't know. You see symmetric symmetric power, of course, it's a nice thing, but it's at the level of varieties, it's singular, yeah. Like if you take a surface, there is a resolution of singularities, and that's a space, the correct space for the action of Heisenberg, which probably will appear at some point.
Oh yes.
Oh yes.
Yeah, but as you formulated it, there is no kind of a shadow of this resolution of singularity. So that's
there is.
No, the resolution of
already
singularities, no. But the Heisenberg action, yes.
Sorry, Rina, just a second.
Yeah, okay.
This is important. When we talk about nth-symmetric power of T, we're really talking about Sn equivariant T. We're talking about the smooth stack, not about the singular quotient. And a smooth stack is already, in some sense, a resolution of singularity.
Okay, good point. Thanks, Timothy. Yeah, okay.
Yes. So what? And then So what I'm going to talk about today is we have proved this conjecture via an explicit isomorphisms back and forth, and also our construction works for any DG category T, not only for smooth. So we don't require that. So, and the first thing that is different in our approach is that instead of considering SN equivariant modules over the tensor, we're starting with a DG category T. So instead of considering SN equivariant modules over the tensor nth tensor power of T, which is a Kapranov-Gunter construction, we consider all modules. So all modules over the category that was introduced by Genya Koppensteiner and Logvinenko in 21. That's so category A smash product G. So in our case, A will be a nth tensor power of a category A, and G will be Sn. But this works for any, so construction exists for any DG category. And now one caveat, there needs to be a strong action of a finite group G. Now a strong action of a group on a category is a thing that does not easily happen in any geometric context, but the action of Sn on a tensor product of n copies of the same category is strong. So it works. And so they define this DG category as a category where objects are the same as objects of A, and homes from A to B are pairs of are generated by pairs of an element G of G and alpha in home from GA to B. And then when you want to compose two such pairs, then when G goes so alpha comma G composition beta comma H, then when as G goes through B, so it acts on through beta, it acts on beta. So it's alpha composition G beta comma GH. And they prove a theorem that there are mutually inverse isomorphism of categories, not even equivalences, but we can do that because objects of this smash category is the same as objects of A. Is that the category of modules over this category is isomorphic to the category of G equivalent modules over A. And same and on the level of perfect modules.
What means H? Sorry.
H perf homologically perfect.
Okay.
So
H projective and perfect.
Yep. So
and here the perfectness that on the left hand side that's supposed to be that's for the smash products that's projected in. I guess here the group G is a finite group, or it's much more general.
G is a finite group.
Okay. And assume that the G action really doesn't destroy any projectivity of the.
Probably not
theorist.
Not H projectivity.
I think there is confusion here. H projectivity is just some abstract digi-categorical nonsense. It just means that our objects are like projective objects. They're homologically correct. This is not about sort of this is not kind of a replacement for or is replaced by. It's not replaced by G equivariance. It's just like when you construct a derived category, you want to take complexes of injective or projective objects in order to get the right morphisms.
On the right hand side, one could have those are A injective, and the left hand that is A direct product with G injective.
Yeah, so we are not taking actually projective modules here. We are taking objects of derived category that act so that work homologically as if they were projective resolutions in the sense that homes from them to acyclic complexes are acyclic. So this is not broken by G equivariance. Sorry, Zhongzhu, have I answered your question?
Yes, but okay. I have been thinking very trivial one that A is just a vector space and A is a field and G is a finite group. In particular, that the characteristic of the A and divides the order of the group. So there are issues here.
I would say that for us, the ground field is usually algebraically close to characteristic zero.
So that's
why I was asking. In that case, the group really doesn't destroy the projectivity.
Yes, or at least we should always require that the characteristic of the base field is relatively prime to the order of the finite group G.
Yeah, that's good. Yes.
So, and yeah, here's our theorem. Then, if we have a small G category, then we have two inverse isomorphisms like this, and then. Why do we care? So the explicit nature of our isomorphisms allows us to pull a number of structures from the right-hand side to the left-hand side. So the right-hand side is a symmetric algebra over some, well, admittedly big, but still a vector space. So it's a Hopf algebra. And then, moreover, it is a free lambda ring generated by the Hochschild homology of A. And it is a Fock space for a Heisenberg algebra of, again, a Heisenberg algebra of the Hochschild homology of A. And we can now find the counterparts of all these structures on the left-hand side. So let me explain how we prove it. So here is a reminder on twisted Hochschild homology. So we define the Hochschild complex for A twisted by an endofunctor, so invertible endofunctor T. As a usual Hochschild homology, except that one term that in the differential is changed when alpha m in the Hochschild chain travels to the the cyclic part, when alpha m goes to the front of the chain, we apply T to it. And then this is how we prove the theorem then. So the first the first part is the analog of the classic result about the results about the this orbifold decomposition. So we establish an isomorphism of the Hochschild homology of SNA with the direct sum over all elements of the symmetric group of Hochschild homology of Hochschild complex of A, so tensor power of nth tensor power of A, twisted by sigma, where sigma is an element of the symmetric group. We take this direct sum over all elements of the symmetric group and take coinvariance under the action of Sn. And then, so these are all maps, chain maps between Hochschild complexes. So they are homotopy equivalences rather than isomorphisms. So it's isomorphism on the cohomology. And then, so the two vertical lines are those are just some technical manipulations with Hochschild complexes. What happens here is we're turning a sum over all elements of the symmetric group and coinvariance invariant by the centralizer of a representative in the summand. So in conjugacy classes are enumerated by an ordered partition of n, so lambda underlying lambda is an unordered partition. And then for every underlying lambda, we choose a representative sigma sub lambda. So it doesn't matter much which representative, so we prefer the one where the cycles are all like I plus 1, I plus 2, and so on, and they go in the ascending order of length. Okay, it doesn't much matter. We just choose sigma sub lambda for every lambda.
So basically, just they choose each conjugacy class choose one representative.
Yes.
Right.
Exactly. Yeah, and then for every and then we for every conjugacy class for every fixed lambda we establish homotopy equivalences between this Hochschild complex of A tensor n twisted by sigma lambda coinvariance of centralizer of sigma lambda. Now, with the a certain symmetric power of Hochschild complex of A. So now what's this thing? Is that in a lambda, so what's the centralizer of sigma sub lambda? If you now if lambda well, that it's all the power, it consists of all the powers of sigma sub lambda. But also if lambda has two elements of equal length, so if partition lambda has two terms that are equal, if we have two cycles in equal length in this decomposition, so we can also interchange them. So that would also be in the centralizer. So we split sigma sub lambda into groups of cycles of the same length. And so for each I, let R sub I be how many elements, so how many times I is in the partition lambda. And then, so for every I, for every cycle, so this Hochschild homology of A tensor n twisted by sigma sub lambda is isomorphic to a tensor product of Hochschild homology of A, one copy of Hochschild complex of A for every cycle. But since we are taking coinvariance by a group that can interchange cycles of same length, we need to symmetrize. So we need to symmetrize copies of HC of A that correspond to cycles of the same length. And that's what symmetric power of R of lambda represents. We take a product of HC of A, one for every cycle, and then we symmetrize the ones that correspond to cycles of the same length. So in the notation with T, C of T, it is, so as Jan said, T's are for the bookkeeping. So we attach a T sub, well, I mean a power of T, but actually it should better be T with an index corresponding to the length of the cycle. And then T's, so these T's are symmetric with respect to each other. So we have just a power of T sub k for several elements of cycle, of cycle of length k. But powers, so cycles of different powers do not do not mix with each other. So now, how we're going to do this? So first, the maps nu and xi. So between the Hochschild homology of a smash product of a category group and a coinvariance inside a sum over all elements of a group, HCA twisted by G. So the first map is, so we start, maps in A smash G are, well, linear combinations of, but we can just as well consider, so define this map on just monomials of pairs of alpha 0, which is a map in A, and sigma 0, which is an element in G. And so, we are sending them to the following thing. So it's almost like we are moving all the sigmas to the left, so to the left through all the alphas. So alpha m is acted upon by sigma m inverse, alpha m minus 1 by both sigma m inverse and sigma m minus 1 inverse, to all the way up to alpha 0. That is that we apply the inverse of the product of all sigmas too. And then note that alphas are not composable. Alpha I, so under this chain, alphas are morphisms. So there are objects of A, some A0, A1, A2, and alpha 0 is from GA1 to A0. And alpha 2 from GA2 to A1. But if you, so they become composable when you apply different sigmas to all of them. Well, and then, sorry, not G here, and I cannot erase. So sigma 0, A1 to A0, and sigma 1, A2 to A1. So if you apply sigma 1 inverse to alpha 1, it is then a map from A2 to sigma 1 inverse A1. And when you apply sigma 0, so sigma 1 inverse sigma 0 inverse to A0, it is a map now from sigma inverse A1 to sigma 1 inverse sigma 0 inverse A0, and it becomes composable with the next map over. So this is a chain in so our category. So this is should be a tensor n smash s. And so if it is a n should be the same as a n here.
But of course, this decomposition works for any group G, actually.
Well, this decomposition works, but I mean, if it's actually type in our paper, it should be A here. If it is a group G acting on any A, this is not A to the n, this is just A then. The point, the point is that it is almost composable except between this one and this one. And there we need to twist by this element. So we land in the Hochschild chains of A twisted by by this element of G, the inverse of the product of all sigmas. And so the map C to the other side, that's we take coinvariants and then we symmetrize. So symmetrize them. So we map an element X to the sum of all GX. So any class in any element, well, probably one over the size of G. So any we can choose any representative in the coinvariant class. This map is well defined on the coinvariant classes. So we uncoinvariant it, and then we apply a map that sends every chain to a chain where we apply this element to alpha 0. So we get essentially G inverse alpha 0, comma G inverse. And then tensor, and then other alphas don't get an element of a group. So just alpha 1 identity, alpha 2 identity, and so on. So, and these maps are homotopic, mutually inverse homotopy equivalences. Then the pair of vertical maps are so quite technical. So it's just we not sure this is okay.
I mean, the vertical arrows are really straightforward because we take coinvariance by the action of the group. So in every and the group acts by conjugating. So every Hochschild homology with respect to category twisted by any element is isomorphic Hochschild homology of this element of the conjugation of this element. So that's why we pass from sum over all elements of the group to sum over just conjugacy classes.
Yeah, just a technical thing. So then the most interesting part is this part. How how do we turn twisted Hochschild homology of a tensor power of A into a tensor product of several copies of Hochschild complexes of just a single A. So let's first consider the situation where we have one cycle. So let T be the cycle of length n, just 1 goes to 2 and 2 goes to 3 and n goes to 1. And then we construct a pair of two homotopy equivalences, F and G, so that we call F and G. And then, so here in this diagram, we have F sub lambda, where lambda is a partition, and G sub lambda, where lambda is a partition. And those are made out of individual instances of F and G, and then Eilenberg-Zilber maps between Hochschild homology of a tensor product versus tensor product of Hochschild homologies, so the Shufflin map, and the Alexander-Whitney map, which is the homotopy inverse to that. So, but yeah, we make these F lambda and G lambda out of individual instances of those F and G. So let's talk about what those, so that so what those F and G are. Now, so we do construct explicitly all this system of F and G and homotopy between F, G and identity, and homotopy between GF and identity. And if we work with normalized Hochschild complexes, so if we if we mod out by elements that have one, or since we're working with category, would be identity somewhere in the chain except at the first place, then the homotopy psi actually disappears. Then FG equals identity. However, so there is a, then if once FG equals identity, we can find so we for certain homotopy calculations, basically for perturbation, so for deformation of the differential, it is useful to have so-called side conditions. So we have FG and a homotopy between GF and identity, and FG equals identity, and side conditions say that F times phi equals 0, phi times G equals 0, and phi squared equals 0. We don't have this here. So we do have some some weaker relations that still allow us to do some basically to extend those maps to mixed complexes. So in order to describe the maps F and G, I need to introduce some notation, because a Hochschild chain in A tensor n twisted by T, well, it's a Hochschild chain is a tensor product of M elements, but now every element, every morphism in A tensor n is a tensor product of n morphisms. So we'd like to write them in a matrix where so this is an element, so this is a morphism in AN. So every row is a single morphism in AN, and the chain is the chain of rows. So the tensor product between rows is in the Hochschild complex, and tensor product within a row is a tensor product in A tensor n. And then note that, so this is Hochschild homology of a category. So these are morphisms. And in order for, well, in the definition of Hochschild homology of a category, or in order for the Hochschild differential to work, they have to be composable. So like the first row and the second row have to be composable. So the arrows in this picture show the order in which the morphisms should be composable in this whole system. Because when we take the last row, the row number n, right? And here, the way, so for these computations, start the enumeration with 1 and not 0, it really doesn't matter. So when the last row goes to stand before the first row, it gets shifted by t, so by the long cycle. So AM1 so now goes to the second position. So AM1 has to be composable with A12, and so on. So in fact, we have a big cycle of length Mn and a chain of alpha ij that are composable in the order determined by this big cycle. So, and whatever we do to the Hochschild complex, the alphas must stay in that order because otherwise they just would not be composable. So the map F is from Hochschild homology of An twisted by T to just Hochschild complex of A, not twisted by anything. So we are taking this matrix thing and we're turning it into just a chain in A. And the way we're doing it is we sum over all columns of this matrix. And for every column, we leave the entries from the second row down intact. And all the other entries from the matrix we gather in the first position in the order that they are composable in. So here is an example with 3x2 matrix. So there will be one summand where we have beta and gamma by themselves. And then the only thing that can go to the first position is this delta epsilon zeta alpha. And plus the same thing for the second column. Note that if our category is not a category, if it's an algebra, and if it's a commutative algebra, then the natural map that makes this work is not this one, is the one that multiplies all the elements in the first row and puts them first, all the elements of the second row and all the elements of the last row. So this is just a different homotopy equivalence. And the map G is the map that must take a single column and make a matrix. So by putting, so what we are going to do is we are going to place the entries from this column into the matrix so that every row has exactly one entry. That's one condition. And the second condition is that the one entry in the top row is always going to be in the first place. Well, that makes sense because after all that, we are taking coinvariance by the action of the long cycle. So we are allowed to cyclically permute the column of this matrix and it will be the same. So just pick the representative where this entry in the first column, so in the first row is in the first column. Now, so it is better showed with example. So first of all, we place alpha 1 in the first row, right here in the top left, but we don't necessarily place alpha 2 in the second row. We place some element in the second row, so we can mark some position where there will be an alpha. So these are all ways to choose one element in every row, but then we must fill those positions so that alphas still go 1, 2, 3, 4 if we go down the first column and then down the second column. So for example, here, we have alpha 1 identity, alpha 2 identity, but then in the third row, we have identity alpha 4, and then alpha 3 identity. Now, if we read the numbers of alphas from the top down, we get a permutation. And this summand comes with the sign of this permutation. So these are explicitly what the maps F and G look like. And I'm not going to describe the homotopics in an explicit way because I don't have another hour. In fact, my 1 hour has just come to an end. Now, let me just say what results about the left-hand side. So about the total Hochschild homology of S and A, we can get with these isomorphisms. So Hopf algebra structure is done by just first shuffle product. So that's the Allenberg-Zilber map, the Kunet formula, and then induction. So from we have tensor product of n copies of A symmetrized, tensor copies of m copies of A symmetrized. We map that to a tensor product of n plus m copies of A. We are not saying that this is the Hopf algebra structure you get by first mapping this complex. Actually, no. On the homology, it is exactly what you get when you first apply F, then do multiplication in the symmetric algebra, and then pull it back using G. On the homology, yes. So, but we establish this on the level. So on the level of Hochschild complexes, like in the bottom row, it is just maps that commute with G. So co-multiplication is doing things in the opposite order. So we first restrict. So from Sn to Si cross S I bar, where I and I bar is sum over all the ways to split the set 1 through n into two sets of certain order. And then we do the Alexander-Whitney map, which is the homotopy inverse to Eilenberg-Zilber map. So it is a standard Hochschild complex thing to disentangle this into S one size A, tensor S the other size A. So Hopf algebra structure, then the Fock space structure was done by Gyangyi and Logvinenko. So, and in fact, this is how we, as in Timothy, myself, and Volodya Baranovsky came over this idea, is that Gyangyi, Logvinenko, and Clemens Koppensteiner were studying a categorical Heisenberg algebra action. So its decategorification of this is what we get on this total Hochschild homology of S and A, and it corresponds to the classic Heisenberg algebra action on the symmetric algebra on the right. And finally, the lambda ring structure. The thing is that the result with topological K theory allows was described by Siegel in a handwritten note and developed and expanded by Wei-Chan Wang in 2020, I think, is that so they establish an equivalence of lambda rings, but the lambda ring structure that they have on the right-hand side relies on the lambda ring structure on the topological K-theory of X. And then one uses it then to construct the lambda ring structure on the left-hand side. Now, the right-hand side, especially so in our case, so well, any symmetric algebra tensor, this TKT, has a lambda ring structure. Well, it is a free lambda ring generated by V. Now, if V already itself has a lambda ring structure, then we can also define another lambda ring structure on this using the lambda ring structure on V. And this is not and this is going to be isomorphic. So the lambda ring structure that we get on this symmetric algebra is so using the lambda ring structure of the K-theory is isomorphic to the free structure. So because basically we take so we split the K-theory into eigenspaces for Adams operators, and then so do a coordinate change. So rescale every space according to what there should be. But however, in our non-commutative situation, we don't have any lambda ring structure on the Hochschild homology on A. But we do still have the free lambda ring structure on the symmetric algebra. And we can, so we can pull it then to the left-hand side, to the direct sum of all, so total Hochschild homology of direct sum of all S and A, and get some lambda ring structure here. So, however, so we do not. So there is no chance to start with start with an A and suddenly have some grading, so some additional grading on its Hochschild homology that would correspond to the cohomological grading for some X. So this is the way it happens in the commutative case. Yeah, but interestingly enough is that if we try to pretend that our HH of A, so if we try to replicate the process, the way we get Adams operations on the K-theory using our morphisms, we get the free structure. So we don't really get, so we get the trivial structure on HHA and the free structure on the symmetric algebra. So, but yeah, not surprising because pulling cohomological grading from pulling additional cohomological gradient on HHH would have been strange and out of nowhere. So I have a list of some references which I referenced the most in this talk, and thank you everyone.
All right, thank you for the talk. Any questions?
Probably a very simple question. I'll go back to the graduate algebra class from the very beginning. That this there is a Bernstein counting formula for counting the number of orbits when you have a finite group acting on a set.
Okay.
So I felt that some of the formula earlier, it's of that version. You have a same, especially the second line.
So second formula here.
Yeah,
Or the second slide.
yeah, the second line over there. So this one's taking the sum over all g's, and
Yeah.
you can see the last line is even
I
closer
see.
to the
So those we
Bernstein
can,
counting formula.
yeah. So basically the middle column in this diagram. So sum over all elements of
Conjugacy
Sn and
classes, yes.
coinvariance by Sn, and the sum over conjugacy classes, and then each separately coinvariance by its centralizer. This kind of thing.
Yeah, that's what I felt, that if I just trivialize everything to a very basic, just my space is a finite set, my group is acting on that space. So the computation, whether that gives exactly what Bernstein counting formula.
Yep, probably.
Okay, well,
Okay.
that'll be interesting. I'll talk to you later on this.
Okay.
More questions? So do you have a version about periodic cyclic homology?
We are working on it. We almost have it. So we can. Currently we have a version of the isomorphism. So FG isomorphism. So we are smoothing out the details for new and Xi pair.
And also, I accepted this thematic explanation at the very beginning, but now I'm a bit confused. Your category A is no longer smooth. Yeah, it's
Yes.
just. Then my remark, I return to my question or remark about resolution of singularities. Because for me, kind of a test, I don't know, relevant to what you've done or not, but the test is the Götzsche formula, which comes from the relation of the category of perverse sheaves, for a resolution of singularity. So it's smooth. So then it's basically just more or less local systems, but for symmetric power it's not. And so you have an isomorphism, but if you want to get the Götzsche formula, as Nakajima did like 30 or something years, 35 maybe years ago, then you need one more thing which you don't have. And so I'm kind of a bit confused whether the resolution of singularities are handled.
May I ask which thing we don't have? You just
There is no, okay, actually it's, maybe you do, but the question is, assuming that there is an analog of your formula for HP, yeah? So then we have something at the level of cohomology, but at the level, there are two things in, say, I don't know, symplectic resolution of singularities, like the simplest case is this Nakajima business, or more generally, the school and branch. You have your some category or whatever space, which is a symmetric power of your space, whatever x at the very beginning. I don't remember. All right, this is one thing. And the cohomological computations are very simple, and they are essentially reduces to your formula, that something is a symmetric power of the cohomology of the space, whatever x, without quotienting, and then we take just invariant and the variant. Okay, this is one story. But if I want to connect it to the cohomology of the resolution of singularities, it's not trivial thing. There should be some extra functor from some extra category. I don't know.
I agree. Can I try to say my understanding of it? The Goethe formula and what Nakajima did, they were working with something slightly different. They were working with the Hilbert scheme of points on the surface, which is specifically for surfaces. There is a Hilbert scheme, which is a nice, as you know, I'm sure, geometrical resolution of the quotient of the singular symmetric power. However, this part of the story, of course, completely does not generalize to higher dimensions because Hilbert schemes for threefolds and so on are awful. However, what we did is I mean, and this is not just us. Andreas Krug has been working on this for since like 2015. The idea is that to get this to work in higher dimensions, you instead of working with Hilbert scheme of points, you work with the quotient stack. And the point here is somehow that when the group is as nice as symmetric group acting on a symmetric power, our result tells you that the Hochschild homology of the, well, direct sum of Hochschild homologies of this symmetric quotient stacks, well, non-commutative versions, so the symmetric power of a category can still have a Goethe-like formula connecting it to the sort of Hochschild, well, this symmetric ring of the original Hochschild or periodic homology of the original category. I mean, even, and so the thing is, this is a very non-commutative result. We do not try to take a resolution of singularities. We simply work with the quotient stack of the original space. And it turns out, for some strange reason, that even if the original non-commutative space A is awful, which means it's not smooth and proper, this formula still holds.
Yeah, I understand, but you see the point, kind of my confusion or whatever. Hold on, let me finish. Is that if you work with quotient stacking in the Nakajima framework, you get McDonald formula, generating function for Poincare polynomials of quotient stacks. But a Goethe formula is different. If you look at it, they look similarly, and you can use formula for stacks in order to get the formula for the resolution of singularities, but they are different. And so that's, I would like, so I would be happy to see that if you can handle this difference, because this difference is a difference between kind of local systems and perverse shifts. So yeah, that's kind of.
Thank you. This is a very interesting comment. So, yes, just for me to remember to look it up later properly. I'm familiar with Goethe formula, but you are saying that I should also look up McDonald formula, and that's what you get.
You can find it's a very nice old paper by Ian McDonald of 1962. If you like, I can say, but you can find it on the internet. It's called the Poincare polynomial of a symmetric product. It's very simple, and he explained that there is very little topology. So basically, you take any, I don't know, topological space sufficiently nice, and there is this formula which looks as a Goethe. It's like, or whatever, many other, like, you know, right-hand side for the zeta function, like in the Weyl conjecture. It's a rational function with a quotient, and so in the denominator you have some simple factors with odd Betti numbers. In the denominator, you have similar factors, but with even Betti numbers. And it looks very much like Götz, and you can, using the Chow-Hilbert map from the Hilbert scheme for surfaces, of course, only.
Of course.
To this quotient stacks, you can derive Götz from MacDonald using very simple properties of perverse sheaves, in particular that in that case for the Chow-Hilbert map that the quotient have rational singularities. So basically, if the IC sheaves agree before push forward and after. So it's a very, kind of very simple, but the formula is different. So you can deduce one from another one, but they're different. And so that's resolution of singularities. It's something non-trivial. I'm not sure that it's about resolution of singularities, but at least in the case of symmetric power of a surface, this is the case. Yeah.
Thank you very much. We'll definitely look into it.
Yeah.
All right. Yeah.
Can I comment on my understanding of this problem?
Yeah.
I think that in the singular case there is a disconnect between the Hochschild homology of A. So if A is not a smooth category of something that resolute. So then we need to resolve on both sides. Then the symmetric power of A is not smooth. It's never smooth. But then A itself, so HC of A is also not the right thing to consider. So let's say if A is say an algebra of functions on a smooth affine scheme, then both the left-hand side and the right-hand side have a nice interpretation in terms of some cohomology, K-theory, perverse sheaves, and something, and then the left-hand side is the quotient stack, which is kind of sort of resolution. But if A is not an algebra of functions on a smooth scheme, and if A is specifically is not a smooth DG category itself, then Hochschild homology of A is not the thing that has interpretation in more geometric terms. And
yeah, that's fine, but if
so
A is smooth.
This decomposition is is something that works specifically in Hochschild homology. Is that if Hochschild homology of A is related to other things, then a similar decomposition also holds for these other things. But sometimes, so if A is not a smooth DG category, we need extra steps to relate both sides of this equation to something about
I understand. So it's rather not question to you, but to that paper of 3 people which you mentioned at the very beginning when the category is smooth. Even there, the question is how to handle some other category which morally is a resolution of singularities of symmetric power.
So instead of taking sheaves on the resolution, we take the G equivariant sheaves on the product. I think it's proved that there must
They're
be
different. Yeah, they're different. Yeah. Okay. Yeah. Get it. Okay. Thank you. More questions?
Can I ask what the subscript of T is on slide 9? I believe
it's coinvariance. It's coinvariance by the action of T.
Oh, okay. Are you thinking of T as an endofunctor? It's not a module, right? It's a
yes, endofunctor.
I see.
Where
I think it's slide 9. Yeah,
this?
yeah.
Yeah, exactly. Yeah, where looking at, yeah, T is an end functor, but also every end functor is a bimodule. And so specifically when T is an end functor, so I can, so the formulas for the, so, okay, now I lost my cursor. Okay, explicit formulas for the twisted Hochschild homology. So assuming T is an end functor, this is what we mean by HC80. Oh, you're saying why the covariance? Well, T still acts on A. So how does T act on this? Well, you apply T to every alpha.
I see. So you're sort of looking, so covariance, you're looking at like the orbits under this endo functor.
Yeah. So what are covariance? So covariance under a certain action is a quotient by every x minus g acts on x.
I see. Thank you.
You're welcome. So yeah, actually, no, at that point, this is not an end functor. T acts on the vector space, or rather on the chain complex of Hochschild homology. Like here, this left-hand side is so this is a vector space. So we just have a linear transformation acting on a vector. No, sorry, not linear. Just a map acting on a vector space.
All right. Any more questions? Well, if not, thank you very much. And I recall in the next week we'll have mini course of David Agayota. So 3 times. Probably Lina will send. I hope Lina will send today an announcement. All right. Thank you, Rina. Thanks.
Thank you.